So the next presentation's a little bit different than the other ones because I'm going to talk a little bit more about workflow and where things are in the new software. Well, actually, not using the new software. This is something I could have probably done on the microscope just as well. This is actually my webinar slides I gave I think back in I think it was November. So if you watch the webinar, you can tune out if you want to. But let's talk about Apex 2.0 for EBSD, what's new, key features, and why we did some things differently than Team. So, of course, first I have to kind of talk about what is Apex, of course. Let me go ahead and get my pointer back up. And so Apex is our next generation of software, basically replacing Team. Uh, Team was started, I think, in like 2007 is when development for Team started. And when it started as a 32-bit software. So Apex is our follow-up to Team, basically starting fresh. We started over at a 64-bit platform. You know, computer speed and power is just so much different. But we said, hey, let's go ahead and basically start over. So we use this as our data collection software for the analysis of your materials, and it does a good job. Of course, it's made to be highly productive and easy to use, and much more real-time feedback than Team could give you, including reviewing data at the same time. So Apex EBSD software was released to customers, I think, in October-ish. Don't hold me to that. And of course, it's basically the same in most ways to Team. It includes things like the CI and the triplet indexing and the smart detector optimization we'll talk about in the afternoon and all that kind of fun stuff. It's all in there. It's not, don't go waste too much time talking about that. The main difference with Apex is we went to the ribbon bar structure. Um, if you've ever used Team and done some higher level stuff, it can be a little clunky in some ways. What I mean by that is we wanted these buttons to be functional as well as very telling. So here you can see that we have this ribbon bar structure and this kind of this tab structure, and this is basically us saying, hey, Microsoft is better at doing UIs than us. They have entire research departments who do UI work. We're a smaller company. We can fiddle with UIs, but hey, they know better than we do. Let's go ahead and basically copy them in some aspects. So you look here, you can see that you basically have different modes, so to speak, of using it. And when you change these, you get this contextualized bar that changes depending on what you're doing. So here you can see like things like the Huff tab is just Huff. And this is kind of an example here of if I wanted to bring up the Huff tab in Team, I have to go to the right-hand side. That little slide bar would come out. I would click. I would scroll down. I would click on what's called the Huff tab, and I would scroll down again, and then I click on Full Display. Here, I click on Huff, and all my Huff parameters are just there. So again, we kind of make things much more easily discoverable for the user instead of kind of everything being hidden behind menus. The biggest difference really is going to be the data management side of Apex versus Team. One, you can save the data wherever you want. So you can specify a drive or a folder location. Again, you can do you can put the Apex data where you want it to. Users can name it and kind of make the data nodes wherever you want. And of course, users can move this data easily around. Again, all the data is put into what's called an HDF file, and it's highly portable. It's just a file. In this case here, I call this project here Apex EBSD, and it's just one file. I just copy that over to my flash drive. I can move around and go to any Apex system, click on that, and bring that data up. So I can easily kind of move that data around. Of course, it's the same thing here. You always can kind of change your names, and actually you can actually go back to nodes, which is something new that again a Team could not do. So why this HDF file format? It basically is a data structure that allows itself to be imported in other programs very easily. So patches exist for opening the HDF file format in many open source data kind of packages. So things like QGIS, Python, MATLAB, IDL, R, Mathematica, and who knows what else at this point can very easily open up the HDF file format inside of them. And again, you actually look at this. So this was me, playing with QGIS because that's literally the file that named here. and I was playing around with this data inside of QGIS, and you can see that, I click on like carbon. This is going to be an EDS map, and I can see, okay, it's XY, it's 168 by 217 pixels. It's chunked. Here's my storage allocation. Again, all this information is basically there to make it easier for you to deal with, because one of the things we want you to do is we firmly believe that our data analysis package is the best data analysis for EBSD data. We also realize that people often want to know how things work to such a degree they do want to do it themselves. Well, if you want that, you need the data in such a way you can do whatever you want with it. Here it is. You have access to the data at such a level that it's all available for you to do whatever you want to do. And that was kind of one of our big design decisions here, is that, you know, you know, some companies, when you collect their data, you're kind of locked to their what they want to do. We really wanted our data to be like, do whatever you want with it, wherever you want with it, and that was kind of the idea here. One of the actual big things with this is it allows you to, like, move back to a sample. So in this case here, I had, sample 1, sample 2, sample 3. I went down to sample 2. I wanted to collect more data in sample area 1. I can just sample 1. I can just go back to it now. I click on sample. I go back up there. I can do that. In team, I have to make sample 3, and then I had to annotate it in such a way to know that sample 3 is actually the same as sample 1. But I couldn't add that to that data node. So it allowed this disassociation of your data inside your own project. But now that we can go back and forth, it allows much cleaner projects, and again helps you kind of not get lost, because again, I think one of the things that scientists you learn is that sometimes we be sloppy collecting data, and the cleaner that we can make things, it makes it more easier for us to understand again what we got that data. I mean, it can be, you can waste hours on a microscope just by kind of forgetting what you did and where. So take good notes, right? So for EBSD, we've kind of with this tab structure here of a couple of different things. It's basically workflow related. So we have this camera tab, and the camera tab is basically made for you to easily optimize your camera with everything right in front of your face. So go ahead, and I'll show that later on. The pattern tab is kind of more for like your single point work. So let's say I'm doing some sort of diffusion experiment, and I want to know the exact orientation that I'm on. I'll go ahead and do the pattern tab and to kind of do that there again, kind of like more like a point and click mode. The scan tab, the UI set up more of a mapping montaging kind of thing, so I can quickly do maps and have maps going quickly. And of course, the phase tab is more of combining EBSD and EDS for doing what's called true phase analysis. So if we say, okay, what do I actually have here? And of course, the Huff tab is made for optimizing Huff parameters. The final tab is a little bit different than team. The calibration tab here is open for all users, so keep that in mind, lab managers. But it allows you to quickly change and optimize and go back and forth between different calibration profiles. This is incredibly useful, and I think you guys have already found use for that, and that's again good to hear. You guys do have team Apex, excuse me, on the velocity system. Why the Hikari does use team at this point. Both these systems do have what's called smart camera optimization routines. These routines basically optimize the camera for you using the camera settings. So they are context sensitive. And what I mean by that is if I'm on the single pattern tab or the EDS tab, I have different choices available to me than the mapping tab. So again, in this case, like the EDS tab has like EDS counts mode, which allows me to basically slow down to make sure I get enough EDS counts. I will tell you that manual setup is also available. In general, I do manual setup. Why? It actually gets back to a question I had earlier. When I use any of these smart camera optimization routines, the routine itself has takes something into effect. It says that I need to make sure I'm getting enough grains, and to do so, I zoom out by whatever my mag is to a factor of 4. So let's say I'm at 4000x. What it does is it takes me to 1000x, scans over the area for my background, and then it puts you back to your original magnification. So I do this all automatically if I choose one of these. Now, why does this matter? Well, if I have my sample mounted in epoxy or maybe on the edge of an epoxy mount or whatever, I zoom out, I'm now often scanning either in free space or the material that my epoxy or my mount is in, right? So because of that, I'm going to put an artifact into my background. And that's one of the reasons I kind of avoid this in general is that hey, I want to make sure I have a little bit better control over my background. That said, you can overwrite that background after the fact, but I just kind of like this is why I avoid these. I think you're better, and if you understand these settings, especially for like the Hikari, um, it's better for you to do it because again, you're basically picking and choosing and making a choice instead of saying, hey, algorithm, do it better. All the layouts in Apex are user configurable, so these windows can be popped out. Again, I'm spoiled a little bit. I have a 49-inch curved monitor down the hall, so I can drag and move things around between the two monitors because basically two monitors in one in a very large layout. So I can like pop out my imaging window and just poof that all by itself if I wanted to. Or again, I can go ahead and put these in a tab structure. I can go ahead and put these side by sides. But in general, we have these pre-made layouts. So here you can see this is the phase tab. I can do what's called basic mode or solutions mode, where I can see the pattern, I can see the image, I can see the information all right there for me. But basically, I can quickly kind of make a UI workflow that works for me with all the information available to me, and I can even save these and update them, etc. if I wanted to. The camera tab is relatively straightforward. In general, the way the workflow works on this is I do this kind of acquisition of my imaging here, and then and kind of work my way from in general from right to left, excuse me, from left to right, but not always. So again, this is my image. This is where I can basically pull out my EDS settings, or not EDS, my SEM settings. This is actually where I choose how I take my image. So I talked earlier about the FSD. This is actually where I changed to the FSD. So this little pull down here, I pull down has FSD as well as the Prius. I can go ahead and pull those down and use those as my background image for my EBSD map. I has also my slide controls as well as my basic other controls here in the camera tab. So there's my slide controls for putting my slide in and out, etc. These right here, these little additional pullouts are usually the finer detail settings. So the acquisition here, I pull this out. It has a little bit higher details about like my EDS detector stuff in there. Like this right here controls my SEM imaging collection parameters. So this controls my contrast and my pixel size, my pixel dwell, etc. As I keep going, of course, I have a little bit more kind of more actual EBSD control here. So this is actually capture the pattern and save it kind of thing. Oh, this is actually toggles control between the SEM and the EDAX software. So again, I can basically, okay, here's the SEM, it has control back versus here. This right here is that preset here. I can go ahead and change my camera. Here again, you can see that as this pull-out menu here. This is where stuff is hidden, right? So this right here is my pattern. You can see I have like my pattern tab. I have my indexing parameters, my orientations, etc. Question about does the software show the zone axis indexes on the EBSD patterns? Kind of. I'll probably show that in the afternoon. I can kind of answer that a little bit more specifically. Good question though. Um, so here's where I can choose between things like interplanar angular tolerances. Here I can see the here's this where the value is 3. Again, never change this. No real ever reason to change this. You also can change the ranking factor, so to speak. So if you want to do it a little bit more of a customized method. So by default, we kind of use this vote method, but you also can add things like fit or despacing kind of thing. And again, it's a little bit more complex than most users would do. And of course, there's my layout tab, switching between the different layout modes. One, I will tell you that I did this software. When I did this with the clarity. So you're going to notice the clarity is a square detector. It's not a round phosphor like the other system is. So here you can see this camera tab has basically everything in front of you. So you can have my imaging view. Here is my process pattern. And you can see both the background as well as the raw pattern. Why is this useful? Often users take bad backgrounds, and I'm going to talk about this in the afternoon, but this allows you to see a bad background very easily. With Hikari, you'd have to go over here and you have to turn the background on or off, and it would update the image for you. But this allows you to basically to see both the background, the raw pattern itself, and then the process pattern. So what you're really doing here is it's your raw pattern minus your background equals your process pattern. And again, you can actually see if you messed up your background. How do you mess up your background? Usually it's this button right here, external control. So what you do, a lot of people do on accident, is they have this, they have the EBSD detector in basically point mode. So you're clicked on an area, you go ahead and take a background. Your background is actually that point because you're not scanning, and that would be a bad background. So you actually would see a pattern in the background, and that will cause an artifact in your data. Now, when I actually would do this kind of stuff, when you do these camera optimization routines, again, it zooms out by a factor of 4. The way around that is just click on SEM area right here, and that would allow you to basically do an SEM, basically what your current field of view is. Use that as your background. So again, if you actually do use some of these smart optimization routines, you can go ahead and use the SEM instead. So there's that. So the pattern tab has a couple different options in it than the other tabs. Again, this is basically assuming that you're doing a little bit more of a single pattern work. When you're doing this, we're also assuming you don't want the data recorded because you're trying to find something. So you actually have to physically record the data. So the workflow for this is a little bit different, where you capture your pattern, you index it, and then you would record it if you wanted to. Again, in this kind of mode, by default, we're not saving the data. We're assuming you're looking for something, or basically, you're surveying. So you want to go ahead and record the data yourself. The other thing here is going to be this little tab over here. I forget where I talk about in this presentation, so I do talk in detail about this over here. This is also where you can see the EDS is available. So I click on EDS and I can collect it. Relatively straightforward. So here you can see the kind of answer to your question. I think that I have there from the chat is, do you show the zone axes? And there's your answer. Yes, we do. You can see it just kind of shows up by default. So when it does the indexing, it just kind of says, hey, this is the zone axis you have here. This is the pattern tab. Again, is when you can see the pattern tab. Here's my indexing results. Here's my solution. So this is going to show my vote counts that we talked about with the indexing algorithm. Here's my vote counts. Here's my fits. So here's a little bit more realistic solution here. This is using 8 bands, and I can see it has 56 votes. I mean, it's going to have a CI that's really, really high. In fact, you look down here, might be a little bit hard to see, but here you can see there is CI is 0.82 and a fit is 0.3. I'm assuming you probably can't see that, but that's a very, very high fit. I should feel confident this is the right indexing solution. And I should feel even more confident again, because again, so this right here, these bands and the black ones are the ones the Huff is using. I can see like this band here, this band here, this band here, all correlate to Kikuchi bands that were not used as part of the indexing solution. So again, I should feel highly confident that this is the correct solution, and my CI being high and my fit being low kind of confirms that. This is the phase tab. This is actually what controls what phases I'm using for the indexing. And what I actually can do with this is where the database comes into handy. Now the database, again, there's actually multiple databases included here. So you can see that the AMCS is kind of included by default. I can search by keywords. I can search by lattice systems, et cetera, et cetera. And then go ahead and click on this, automatically updates down here to say what I wanted. So here I'm searching just for ferrite. It popped up ferrite. And I go ahead and click on it and add it over here to this guy over here. Now, highly useful. A lot of new features kind of hidden in here. Of course, if you have a new file or a new material, again, if you're doing what we call like true research, you would have to build your own phase structure, your phase file. To do that, we have this phase file structure generator here, where again, you basically have to have this information from something else, right? So here I can see I have my lattice parameters, I have the angles. You need to get this usually from some other information. So this is where XRD would come in handy. You'd figure out your atomic positions, et cetera, and then you go ahead and basically it would add a reflector list for you to use, and then this reflector optimization is a little bit more complicated, but we generate this reflector list based off of this information, and from that you can go ahead and do this. So in general, we have our own EBSD specific library we've collected over over the years. It's basically the stuff we run into. So the most common stuff and is already basically in our own database. So usually there. The scan tab is made more for mapping. It is a little bit more complex in some ways because it's done on purpose. We've added batch scan mode to Apex. Batch scan does not exist in Team. It exists here because basically for the EBSD with the velocity, you can do a map so fast you're wasting time. So you actually can do multiple maps discretely and kind of all over your sample by doing this batch mode. So I do a sample, I could say, hey, do it here, do it here, do it here, add to the batch. In the end, you basically run the entire batch instead. Over here, there's a couple different tabs. I think we go in detail here. Yep, so this is where I actually choose what kind of map I'm doing. So here's my standard kind of full free map, free form line in montage. So again, here's a free form. I would basically choose what I was doing. A line scan is just that, line scan on the map. And montage, if I click on this, it's going to run me through basically a wizard to set up a large area map using multiple fields. Here is the step size selector. So based on your magnification, this is going to choose coarse, medium, or fine. This allows you to do basically a very quick map, a slow map, or a longer map. So again, in general, this tends to be about, coarse maps tend to be about 10 seconds, while fine maps tend to be closer to about 10 minutes. And of course, you can choose your own step size. So in general, coarse does around, I think, like 30,000 points, medium does around 200,000 points, and fine does around 1.2 million points. So depending on your camera optimization, it could be longer. In general, though, you can click on manual, click up here on the settings here, and quickly add what you want to do for your step size. And it will also show right here how many points you're doing as a step size and the estimated time it's going to take to run that. Again, this is an estimation. So again, here you can see those settings. So it's basically one step ahead of myself here, but of course you can use this. It does you do relatively consistent measurements across multiple scans because again, it basically picks it for you. Again, one of the major differences here is that this value is basically right in your face, right? So you're setting up an EBSD scan, you change your step size, you change your step size by a factor of 2. This actually goes up by a factor of 4, right? So you can quickly add, you can quickly go very, very long map sizes before you realize it. And that basically lets you say, hey, maybe I don't want to do a 0.1 step size because the mapping is going to take me, 12 hours. Okay, let's do 3 microns. This could be 3 minutes. Also in the scan tab, the advanced settings are here. These advanced settings are highly, highly useful in a couple different ways. One, we by default use a hex grid. Go forward real quick. I don't talk about it, I don't think. By default, we use a hex grid for most of our work, and I'll talk about why. This is where I can say, okay, save my orientation, save my health peak, save my patterns. Why would I want to do this here? This allows me to basically say, hey, for some of my materials, I know I'm going to do post-processing on it. I'm not even going to waste my time. I'm just going to save my patterns. I'm going to not save my orientation, my huff peaks. I'm going to do everything post-processing. Or I could go ahead and save the orientations, means to actually index things. Why do we use the hex grid over a square grid? Hex grids are better because they have equidistant center points, and it makes your data less artifact ridden. So if you do a square grid, your center points from basically the center to the outsides are different. And because of that, there's actually an artifact in your data. Usually not that big of an artifact, but it does exist. We do everything by default as a hex grid. I will tell you this makes the programming much more difficult for our programmers, and they would probably much more love if we did everything by square grid, but we're not that nice. One of the other nice things about this up here, the scan configuration is you can see there's X start and Y starts. This is basically defining the top left of your area, but that's not so much important as this X size and Y size is. This allows you to do is quickly basically be consistent across multiple data sets. So I can actually click on this and type in this and say, I want to do 1,000 by 1,000. I type in 1,000 by 1,000. Now it's going to be slightly different than 1,000 because of the step size considerations, but it lets you basically make sure you're doing consistent work across multiple data sets if you're trying to be very, very specific. Also, there's this PC shift down here. I kind of mentioned this earlier that we do a geometric or a fitted one. We can basically added a method here to automatically do a PC shift for you, but you also can do a calibrated one if you want to. Also in the scan tab, again, this is be brought up by changing this over here, and it actually pops up the window to always be here, and that can be highly useful. I feel like I'm missing something. We'll figure it out. This is that batch scan mode. So again, when I add things to a batch scan, it actually will basically save the data to this batch list. The batch list is actually right here, and I can pull it out by clicking on this button here. When I do a batch list, it saves a field of view image as well as my mag, my stage location, et cetera, et cetera. It lets me see what I'm doing here relatively easily. So here I can see I have like 10 scans lined up or whatever. I go ahead and add the batch, move my stage, add the batch. In the end, I click on go, and it's going to run the entire batch of samples unattended. So again, just let me quickly add things to this. Again, this is new here. Actually, a good question. From you're using team, the grid type is stuck with square type when using combo scan. Is that the same with Apex? Yes. The answer is when you combine data sets, you can't really line up hex grid systems easily. So yes, the square type is used in combo scan mode. Good question. And here is the montage mapping area. This slide is actually slightly out of date. I think we've changed this setup a little bit. But this is a mapping module that allows you to do stage movements to do large field of views. This data should look familiar to you. This is a Gibeon meteorite. So automatic stitching of the data into a single file for comprehensive analysis. There's a setup wizard that kind of follows a little bit more step-by-step instructions. It kind of gets around to some of the most common problems that we see um, with Apex. Most of those problems actually tend to be on the microscope side. When we do this kind of this large field mapping mode, there's a lot of assumptions made on the stage movements, and the stage movements are not often as well calibrated as you would expect. So we're basically saying, hey, move one field of view, and then you get a 1% error on that, and they can actually add up really big. Honestly, the biggest issue tends to be tilt. So here you can see this is the montage area. You can say here that it says, hey, let's go ahead and here's kind of your workflow. Here's what you need to do. Go to top left, bottom right, go ahead and set the areas, and it kind of shows you a preview of what you're doing here. Now, when you're doing that, you're going to kind of give you an idea here of what you're looking at. Nice thing here is actually be able to preview this. So you click on preview, it moves through it, and it gets the SEM images over here to show you, hey, how well was my line up before I actually do a full scan. Um, and the reason we can do that is because if it's off a little bit, it can actually be off a lot. Over here, you can see this kind of this tilt area. When you're dealing with EBSD, you're doing a 70-degree tilt. When you're doing with a stage tilt with 70 degrees, and you're trying to move something in the X, Y, and Z direction, this value of stage tilt being off by very little means a lot. And what I mean by that is like a 1-degree error in your stage tilt is going to be almost an entire field of view off in your Y direction. And because of that, you really need to actually measure this. And I can talk about that later on. But actually knowing your tilt, what your true tilt is better than that. So this is why we talk about stage tilt versus a tilt offset to actually get your final tilt in the end. It really is probably the most important step of getting a good combo scan. Yep. I just kind of went through these, but there's also the ability to oversample. The ability to oversample will basically not save the data as one giant hunk of data. It'll save it as a bunch of individual files, so be aware of that. Basically, that's assuming that you think you're better at stitching than we are. It basically says you're going to do it in our software or somebody else's software to deal with. But it does oversample the data. Our end goal here is, depending on resources and stuff, is to allow you to oversample and basically use algorithms to stitch to get rid of all the artifacts you can see with things like, stages not being perfect. But I would tell you that's a lot of work, and it's something we're kind of actively thinking of working on. It's not a top priority right now, but it is on the to-do list. Oh, the next lab is going to be the phase tab. I'll go over this kind of quickly because it's kind of a niche kind of application. This is basically saying, hey, I'm trying to figure out what I have. And this has got a couple different options here. Really, the new one here is going to be this band ID and a little bit more information here about the tab itself. So it does have the ability to do EDS. And let me just kind of skip ahead here. I don't. Okay. Now, one of the main differences of kind of this in general between Team and Apex is I have the ability to turn phases off and on much easier. So in Team, to add a phase, I had to go click on Profile, and then I had to basically search for it and add it to this phase list. And if I wanted to remove it, I could do that relatively simply. But then to add it, I have to research for it, et cetera, et cetera. In Apex, I can basically just click off, and it's still there, but it's not actively being used. So if I have like a map and I'm not really sure what the phase is, I can basically turn a phase on or off and see how it does. Here in the phase tab, I can overpopulate this list and use this as basically a point and click mode to say, hey, do I have the phases I need for the sample? The other thing I do have here is this band ID mode. If you have if you're doing what's called reflector optimization, if you have like a new phase file, You can basically use this band ID, click on it, and then drag over the band and say, oh, this is the 121. They can actually add it to you to the phase list or the phase file itself if the phase is missing. Phase tab again is set up a little bit differently, so you can see things like the EDS sample spectra and the solutions over here. So I said, okay, this sample here, oh, didn't do ID on here, but let's say, oh, I have a nickel peak. Only use my nickel phase. Click on index, and you can only use the nickel phase. Click somewhere else. Maybe I have an iron phase. Say, oh, just use the iron phase. Click on it. Index just using the iron. Also, you can see the lattice parameters and stuff over here. So maybe if I want to change these, I actually can change the lattice parameters and deal with them kind of bouncing back and forth. Yep. One step ahead of myself. Yep. Band ID, again, ahead of myself. So many neat things. Of course, there are other kind of auto smart features kind of hidden behind the scenes. Auto amp time and auto phase determination during mapping. This is different phasing than EBSD. This is one of the things that always drives me nuts with some of our language here. But when we're doing EDS mapping, phasing is just kind of grouping stuff by grouping and saying, oh, this EDS signal is the same. We call it a phase in that case, where it's not actual good language to use. But so the EDS detector can actually automatically find the amp time for you, and then automatically do the grouping, what we call phasing. And of course, again, the auto step up optimization based off of what you're doing. And of course, we'll pick. You can also have it pick the automatically do the step size for you. The Huff tab is the other tab, and basically the Huff tab is small, but it's just not really what we care about here. Basically you can toggle the bands on or off. That's not really what we care about. What we care about is the whole window itself. This is the Huff tab. The parameters you're going to change in the Huff tab are going to be mainly these guys over here. So you can see here's my image, here's my pattern, here is the actual Huff itself. And I can see here that here are kind of my my things. Do I zoom in on that? I do not. So here I can see that this is my theta step. Right now it's at 1. Again, if I'm using the velocity for max speeds, I need to change this to 2. The other thing that I often change down here is going to be the vertical bias. I usually have this around 3 degrees. Again, what that would do is actually a perfect example of this. The vertical bias right now is at 0. If I change to 3, see this Huff guy down here, like right on the edge here, and maybe it's not the best, maybe there's an artifact. I'd say with vertical bias of 3, it's going to say, let's go a little bit higher and find a new line. It's going to probably find this guy instead. So again, it just gets me away from any artifacts I would have on the bottom of the actual Huff itself. Other options here are going to be things like here's where I would change my mask or the amount of peaks I'm using. So again, if I was using a low symmetry material, I would maybe change this maximal peak count here to 9 or 10. And that's what I would be doing that. Here I can see I got a nice good distribution. Again, the other reason I would do this vertical bias again is it gives me a better distribution. So right now I can see that that's maybe not the best pattern, but maybe if I had like a line up here, I would maybe switch this Huff band here for up here if I change my vertical bias to higher. Again, just make sure I have a better distribution of the Huff lines over the entire area, which is just something that tends to give me better information. And then finally, here's the calibration tab. The calibration tab is basically walks you through doing a calibration. So you click on the instruction that says, hey, make sure you're in the middle, etc. So here again, you can see the calibration. I go ahead and click on center beam and capture. It would center my beam in my field of view. This matters because again, your actual work distance would change from top to bottom. So you want to be in the middle where you're actually focused at. And that's what we click on here. When I do that, it captures an image. If I would do this, it would basically kind of do that. So capture an image, index it, give me the index solution here, and I could see my information down here. So again, I have a nice high CI. You guys aren't going to be able to see that. It's 0.82 versus a fit of 0.4. Now when I do this, I would go ahead and tune it and then record it, and it would go ahead and save it as a calibration point. We also now save the patterns with that. So I actually can go back and recheck and tune these if I wanted to, because we saved the patterns for the calibration. There we go. I click on record, it adds it to the list here, and that's what we're looking at. Now, when I do this calibration, honestly, the key thing to look at here is going to be the error bars. Now, here you can see that I have X star, Y star, and Z star values, and then I have these values here that are errors. When I look at these errors, you can see that they're usually relatively low. And here you can see this is nice lazy calibration of 3 points. Here you can see that I have this guy's a little bit off trend. You can see the error is a little bit high. I can either maybe redo this one and say, hey, this should be better, or I can maybe just retune it and say maybe I didn't retune it good enough. But again, if these error bars are these errors are higher than 2%, I'd usually kick it out. So kind of two value there is what I use as a value, saying, hey, I don't like it. In general, the value that matters the most is going to be the Y star error. So this is the Z star error. The Y star error is actually the really one that matters. And again, actually click on these down here. It's going to highlight the image and show you where these patterns are. So here again, you can see this guy is slightly off. I can delete it in this case. I think that's what I do. I don't do that shit here. So yeah, so the calibration tab here is useful again because I can actually add or remove points. The nice thing about this is I can do a couple different things here. Here you can see I have this profile bar. So right now I'm saying I'm doing a clarity. Now, how often should I be doing calibrations? Almost never. Again, the calibrations you do is basically setting up the reference frame for the camera versus the pole piece. Those things should never really move, right? I work it a little bit differently than most people because I'm probably changing the EBSD detectors once or twice a week. So instead of rerunning calibrations, I actually can save calibration profiles. What would be the other reasons I would want to save calibration profiles? Well, when I'm doing this, you can see my detector in this case is usually all the way in. Uh, some stages will have attachments to them, like either a tensile stage or a heating stage. What it means that is I usually can't put my detector all the way in; it has to be slightly out. So what I would do in that case is I put my slide in all to a certain distance, and then I can actually change that to a different calibration profile instead of making a new one. I just make it once, and I can go ahead and change back and forth. The other thing you could do in this case is you actually can make like a TKD specific calibration profile. So usually we kind of use this optimal operating range for, let's say, 8 working distance down to like 20 or something. Your calibration profiles for that. For TKD, you're often at much lower working distances that may not be covered by your typical calibration. So you actually can make your own calibration file just for TKD from, let's say, 3 millimeters to 7 or 8. And then you have a very much more well-defined calibration profile for those lower working distances to do things like TKD work. So in general, you can see that we've kind of changed the workflow and the look of new software from a team to Apex to make it much more, again, intuitive and user friendly. We hope, and also you kind of made it much more easy to use and much more in your face, so to speak. So all the information is there, not hidden from you. Monitors are bigger nowadays, right? You have more real estate to show things. We also give you the ability to put things where you want to. So we hope that all these features basically make the software easier for you to use, and basically, hopefully you like it better. So that's kind of what I got for Apex, guys. So at this point, questions, comments, concerns, complaints, again, I take them all.